And we'll go ahead and get started. As you all know, and I'm going to share my screen, you all, I think every one of you has been involved in the last session, I believe, where we discussed, and let me just see if I can bring up, I'm running two monitors, so let me be sure. Let me ask you, I have the textbook up on my secondary monitor. Can you see the chapters here?
Not yet.
Can't see it, Bob. It should have a green or a red ring or a red outline around it for us to be able to visualize that particular video.
Well, I'm trying to show chapters. You don't see chapter 5?
No.
Just see your folders on your desktop.
Yeah, it's a desktop.
Okay, so I tell you what, then I think what I need to do is move it over to the main screen. I mean, this is one of the concerns I have. I generally don't have my, see if it'll move over.
If you say share screen, you could then hit share
You
screen,
see
and then you could pick then whatever
Yeah,
screen
no, I
you
had,
want.
I did hit share screen.
There we are. Yep.
Looks good,
So
Bob.
now
Looks
you
good.
see it. Okay. But what I wanted to do is a quick review. Let me change this to, so I have more space here. Let me get rid of the outline. And let me say, I'll keep it at 125, but I want to go over some of the new stuff. But before I even do that, let me give you some updates here. I put this in the WhatsApp chat about the fact that Orange has released version 3.33. They did it at actually my request. I said we really should have a precision recall curve that's very valuable in medicine. And lo and behold, they did. And it's the only new wrinkle I can see in this version. So be aware, to see that curve, you need to download version 3.33. The second thing, if you look at this artwork here in the upper left, and this is for every chapter, that was generated by AI. Y'all, I'm sure, are you familiar with DALL-E 2? Which is text to image from OpenAI, and it's now available for the public. Is everybody familiar with that?
We had some discussion about it on AIFS not too long ago, so yes.
Okay, so it's now available, though. That's only been out to the public about a week. So anyway, we took advantage of it. I'm just trying to tell you that that's the case. We've also consolidated some of the chapters. Initially, I had a chapter on classification and a chapter on regression. Instead, we put both of them into supervised learning, and now we have a chapter on unsupervised learning, and all those subtopics are going into that, so you know. We have an addendum on cheat sheets. There are tons of data science cheat sheets that we can go over that are in an addendum that are helpful. It's kind of like a glossary with tips and shortcuts and explanations. And also initially I had a chapter called Putting It All Together. What I've done is I've sort of disassembled that, and at the end of every chapter, I've put Putting It All Together. In other words, it's a chapter summary with discussion of the most important points, and we'll get to that today. And then I haven't had time to put an exercise because I haven't found a data set that I thought was unique enough. But the point is, at the end of each chapter will be putting it all together for discussion questions for a class, as well as data exercises. And again, I sort of apologize. It seems some days that we're building the airplane as we're flying it, but I think it's a good airplane. I'm proud of it, and I think it continues to get better. So just be aware, I'll probably only be sending you one chapter at a time as we move to the next chapter and you know, dissect it, you know, and try to improve it. Also, I put, I think, 10 classification data sets and 10 regression data sets on GitHub. Let me see if I can copy that and put it in the chat, or at least, let me just see, chat comes up. Yeah, okay. So you can see it here, presumably, if you're seeing my desktop. Let me take that and now I have to find out where oh, there it is. Okay, so you should have that, okay? All right, but what I wanted to do is we have covered most of chapter 5 except for the last section, but I wanted to go over a few changes and a review, because to me, this chapter is about as important as any chapter we're going to go over. The whole idea of data validation is super important. And then I copied 3 of the definitions that Jason Brownlee had for the training data set as the one where you use to fit or train the model. Be aware the computer scientists like to say fit a model. The rest of us say train the model. And then the validation data set is just there to tweak the model with some additional data as you tune the algorithms. Again, you can adjust almost every algorithm and see if it benefits the model. Does it improve its performance? And that's what the validation data set. The test data set is untouched by human hands, so to speak, and it's part of the final model. And it can be data from the original data set, which is okay, but not optimal, or even better, data that's outside that original data set that you split into, say, 70-30 train to test. So I'm going to go speed through this, but I'm relying on you to stop me to say, can we do that one more time? This is just, I'm demonstrating a video here. This is what they're going to look like, a QR code for cross-validation. That's a StatQuest. Some people prefer 3 to 5 minute videos. So I'm going to get through there. Another major concept is model discrimination versus model calibration. Almost everything we've done is called model discrimination. Why? Because when you're talking about discriminating between 2 classes, let's say cancer and benign, or admitted or not admitted, those are 2 classes that shouldn't overlap much. The overlap between that is where you get your false positives, false negatives, and so forth. So if it's perfect discrimination, the 2 don't overlap. And I showed that in a diagram that we'll go over in just a minute. Calibration is really based on individual results, particularly with a probability model like logistic regression, where if it predicts 1, how close to 1 was it? 1 is usually the class you're interested in. Let's say 1 is cancer, 0 is benign. How close was it to 1? Was its prediction of 0 close, or was it 0.2, 0.3? And once you have all those numbers together, you can create a calibration plot. And that is not, so here's one that we're getting to right now that's quite good. The horizontal line, dark line, all that means is if you the model predicts something at 0.8 and the actual results are 0.8, it falls right on that line. But what if the prediction is way below that line or way above that line? And so the significance of this is that in this case, the model calibration and model discrimination are both really excellent, but it can occur where the discrimination is decent, acceptable. But when you look at the calibration, maybe the high end or the low end, it is away from this predicted line, which could mean it overestimates or underestimates, particularly at the high end or the low end. I hope that makes sense, because basically the experts want us to produce a calibration plot. And yet a lot of authors never get around to it. So you ought to park that in the back of your mind. The calibration is also important when you develop a model. Now, I'm going to not go back over odds and probability. I will again tell you, if you have a diagnostic test and you have an issue of prevalence in your community, high or low, and you want to factor that in, and basically you multiply prevalence by the likelihood ratio, and you get the post-test probability, which can really vary depending on how common that disease is in your population. So you have that to refresh your memory. I'm not going to go back over that unless you want me to. So I'm going to quickly go through test and score. We'll go over this every time we have an orange workflow as far as test and score. The predictions we'll go over again when we get the orange workflow. You can do either predictions of the model or individual predictions for each patient, was what you're seeing here. This is a 77-year-old male who had an abnormal cardiac catheterization. The model predicted it to be heart disease at 0.96, very close to 1, in other words. Okay, and to predict at an individual level, this is the workflow here. The confusion matrix, are people comfortable with looking at that? Because keep in mind, sometimes predicted is up here, sometimes predicted is down here. You just have to get used to looking at it, because the whole idea is, again, comparing predicted, what the model is predicting. Let me see, there's another, I guess, Hal needs to get back in here. Predicting what the model predicts versus actual. And actual has to be some kind of ground truth. What does that mean? It means, for instance, let's say you're looking at mammograms trying to tell whether it's predicting cancer or not. Those patients probably had a breast biopsy. That's your ground truth. Biopsy showed cancer or it didn't show cancer. There are many other examples of that. The example we use is cardiac, where you're predicting heart disease, and all of those patients had angiography to look for coronary disease. So you have to have some kind of ground truth. That's your actual, and you're comparing it with predicted. It takes practice, but once you do it, you don't want to live without it, because when you read an article, they really should include the confusion matrix, even if they stick it in a supplement. I still go looking for it, because this is how, let's say they only give you sensitivity, but not specificity, or they don't give you the precision, or they don't give you an F1 score. This is where you go in and calculate it off the confusion matrix. And believe me, and I'm sure David will confirm this, that they cherry pick to some degree. I'm sorry to say, there is no standardized mandatory way to report, say, classification, do or die. It's basically you predict, you're publishing what looks the best. I'm sorry that we're still there. We've always done it. It shouldn't be that way. Editors should have strict criteria. Does somebody have a comment? Okay. And then again, I'm assuming, and I shouldn't assume, that everybody really does understand how you calculate sensitivity, specificity, precision, also known as positive predictive value. These are all important, but you don't really have to memorize them, other than it makes sense when you think about it. Precision, for instance, is true positive over true positive. And what would screw it up? False positives. So you put false positives in the denominator, that's going to reduce, as that number goes up, precision drops. So many of these make perfect sense if you slow down and look at it long enough. And then I used the heart disease prediction data set and did some actual calculations of each of those. But please do go over that. If you have questions, even if it's not today, please email us with the question. So the goal, go ahead.
Bob, before you get into the ROC curve, I want to make a comment to you before the confusion matrix. What's interesting is, a lot of medical journals and medical universities use Jump Pro from SAS, 25,000 US dollars is what it costs. It does not even offer a confusion matrix. It offers an ROC curve only.
Interesting. Yeah, there are a lot of holes in other programs. I mean, I can't emphasize enough that Orange does an awful lot. Is it perfect? No. Does it do everything? No. But it was designed for education. And so for teaching a class like this, it really is unusually good. So the receiver operator curve, yes, came from World War II, where they were trying to predict, is this an airplane or a cloud? And basically it plots, we'll scroll down for a minute, it plots the true positive rate on the y-axis against the false positive rate on the x-axis. If you're doing really well, this curve will be in the upper left. And I want to just emphasize again, when we talked about discrimination, you don't see this in textbooks very often, and yet this is how it should be distributed, or it should be displayed, is notice you've got a healthy, healthy could be benign biopsy and sick could be cancer, but notice you've got overlap. And notice this threshold here that's arbitrarily set at 0.5, but what if you shifted it? It would change things. And that's what we said the last time, that here's an example of that, where at B, this is kind of the best compromise, threshold around 0.5, where recall is pretty good, specificity is pretty good, false positives are 21%. So you go over here where you increase the threshold, recall drops, specificity increases, false positives decrease. You cannot have your cake and eat it. In other words, it's all a compromise. But you do have in Orange the ability to mouse over these different thresholds. You have to calculate, though, you have to go over to the y-axis and calculate sensitivity and go to the x-axis and calculate specificity. And again, when you color in the area under that curve, that's the area under the curve, or AUC. And that, again, is the gold standard for binary classification. When you're trying to discriminate between two classes, the AUC is the most important. But as we hinted, if you have class imbalance, if you have, let's say, 5% cancer and 95% benign, the AUC is no longer as valuable. And that's why we'll talk about the precision recall curve. This is where it's valuable, and I'm simply going to show you a couple examples. This curve that you're seeing looks pretty much like the mirror image of the rock curve, right? Instead of being in the upper left, it's in the upper right. So down at the bottom is recall, at the top is precision. And notice recall up to 1, precision up to 1. So if it's perfect, it would live up in this corner right here. But what happens if you have imbalanced data set? And I mentioned that we do have a data set from Kaggle of stroke patients where 20-to-1 ratio of not stroke to stroke. And so all of a sudden your curve, your PRC is squished down here. And if you color it in, and all I did is paint it, you notice, and if you just guesstimate it, surely that's like 15% of this whole area. They don't spit, this does not generate an area under the PRC. So I'm just guesstimating it to be, say, 15%. But this is in an article with class imbalance. This actually is what they should be publishing. They should be publishing the AUC as well as the AUPRC. All right, and these other orange curves, I think you all can play with. They actually are choices in the drop-down menu for the precision curve. I think to get a better idea of, again, the compromise, say, between precision and recall and the threshold, play with it, move the threshold, and you'll see exactly what happens in the lower left. It'll tell you what the changes are. Calibration plot, I've already hinted, but notice here, this is helpful. This bump up, I think, I forgot, well, this is eta boost, what this is. But for this algorithm, here's the trouble area where it's not very accurate. Well, this might be an important area. So there's just an example of a calibration that wasn't that good. And then here's another one. And again, I really need to redo this to show the 45-degree angle. But look how far down this is. This is so far away. The predicted is so far lower than the actual. It's not funny. So that's, again, how many articles have you all read on machine learning where you actually saw a calibration plot? Not many. All right, well, we're going to go ahead and shift gears into the explain module. The whole idea here is that many of the modules, or algorithms rather, are easier to explain, such as logistic regression, linear regression, naive Bayes. Certainly for logistic regression and linear regression, you can look at coefficients and tell pretty well what the model saw, and you can, with logistic regression, calculate the odds ratio. And so you really know what it's looking at, okay? But what about for XGBoost and Random Forest and others? Simple. We're going to talk about some other ways to do it. And Dave was kind enough to logically add rank widget to this. This is not in that module called explain. If you all remember from last time, if you go to your orange menu on the left, you have to add the explain module. This is where these other widgets we'll talk about, like feature importance widgets, live. But he rightfully added the rank widget, and I'm going to have him explain the workflow and the idea of how the rank widget can be used to see what the algorithm is thinking. Go ahead, Dave.
Okay. So let me just see if I can control the screen here.
Let me stop share, I guess.
All right, guys, let me know if you see something.
Looks
Yeah.
good.
Yeah.
You can see kind of a little widget here, some widgets, right? Is
Yes.
that what you're saying? Okay, good.
Yeah, we see your workflow.
Okay, good. So you're all familiar with the workflows. I'm not quite sure if you've practiced at all the rank widget up until this point. When you get to this point of explaining a model, as Bob was talking about, you know, it's incredibly important always in the world of machine learning. The big thing everybody wants to know out of a model is which factors are the most important, which ones are the weakest, and that'll depend a little bit on which algorithm you're looking at. But the beauty of the rank widget and another widgets we're going to talk about here pretty soon is that you could use them for regression or classification models. Okay, blow that off, sorry. And so it's just this simple rank widget that's over here. And like a lot of things in Orange, you know, you have the file widget, you say, what data do you want to come in? In this case, I have some diabetes data. And then in this case, Orange needs a little help. So what do we put in there? The select columns widget, which I'm sure you're all very familiar with, right? So you need to remind Orange. Sometimes it does very good itself coming out of the file, but sometimes it needs some help knowing, okay, what is the target and what are the features? What are the X factors that we're actually looking at? And then from that point, you could feed it into the learner. In this case, we're using diabetes data 1 or no, if they have diabetes. And also in this logistic regression model, we're using a ridge regression, which is kind of nice because that regularizes the data. I'm sure you might have covered that already, which means that it doesn't care if we have, if these factors are co-correlated with each other. The ridge or the lasso, which I also have an option to pick, will take care of that for us and get rid of the multicollinearity. Then we get into the rank widget. So once it's laid out in this configuration, I can just click on it. And there's some interesting things with the rank widget. First of all, you could see there's 1, 2, 3, 4, 5, 6, 7 different, which are referred to as scoring methods. You might notice right now, I don't have any of them clicked for a very specific purpose. And I'll go back and check them. But I first of all wanted you to see that right now we have the logistic regression learner that's also piped into the rank widget. So right now it's using the logistic regression learner with the ridge, which gives us some regularization, again, getting rid of some multicollinearity. And it's telling me and it's showing me in a Pareto style of rank, are all the factors that are important. And then if I say, all right, no, I'm very interested because it does have some information gain scoring methods. And I might say, okay, what does that look like? And oh, by the way, what does that one look like? So I'm going to click just the top 3, the Gini and 2 information gain type of scores. And then I could see how they compare with the ridge regression scoring. And I could click on the top of here you see over here to the far right.
David, we can't see.
We're not seeing the
anything.
rank open up.
Yeah.
You're not seeing that. Okay, bear with me.
It's gone to the other screen. Yeah, it
Is
has.
it-
Yeah, now we can see it.
Yeah.
Okay, so let me back the truck up here. Let's uncheck. See, right now, it's just showing the rank for the logistic regression, right? And I could double click on the top over here and it could change the scoring from ascending to descending. And then, like I said before, but you couldn't see it, I can then check any one of these 7 different scoring methods: information gain ratio, Gini decrease, and I could check a lot more, but I'm not going to. And then, but the one that's always on the far left is the one that's going to have the perfect Pareto rank. And if I want to then compare what the logistic regression looks like, I just click on the top of that, then that'll prioritize its, ascending order. And I could see then how they compare. And, when you look at different ranking methods, it's always going to be difficult to get every one of them to exactly match up and agree with each other because they're all using a little bit of a different math and a little bit of a different method. All the learners are gonna be that way, and all the different ranking methods are going to be that way. But it's always then very interesting to see, in a data set like this, or at least they are agreeing on the top 3. Well, in this case, they're agreeing on the top factor, that's for sure. They're agreeing also that right after glucose age is the second most important. And then there's a little bit of a disagreement on whether, cholesterol was the 3rd factor or other. And that's where then you say to yourself, all right, which of these learners do I agree with the most? And, then I could, if I want to go back in here, can you also see my workflow in addition to that screen right now, or just the?
Yeah, I can see it.
Both now.
Yeah.
Okay,
Yeah.
so I could go back here to logistic and say, okay, what's going to happen if I change it to lasso, which is, another complementary method. And I could go in here and see if anything happened with the rank, and nothing did happen with it. So that's the basics of the rank widget. And again, what's important to remember is always make sure that you have a select column widget in there to make sure that it knows what are the X's, what are the Y's that you want to include. And then you have some other things that you could change here, select all attributes or just the top 5 or whatever. And like I said before, this rank widget also works directly with regression and or binary classification. And the beauty of the rank widget is it'll work, or watch it not work when I get rid of logistic regression just for kicks. So it'll work even without a specified algorithmic learner, because it already has 7 algorithmic scoring methods already built in, you see? So I don't really need to even attach an algorithm to it, because it already has 7 different scoring methods or algorithms including in it. So I only need the file, select columns to tell what's an X and a Y, and then right away go into the rank. And again, I can do this with classification or regression. And then, you read up on each of these methods and see which ones you feel the most comfortable with. And if you want to just stick with the information gain ones, then you can. And then you get a really good feeling in a very quick way of what's really the most important factors and what are the least important factors with not a whole lot of effort. So that's the beauty of the rank widget. And it's also very explainable to a lot of stakeholders you're going to have.
Yeah.
Could I ask a question, David? It's Hal here. With the rank widget, I see the units, they fluctuate around 1. What are the units, and have they been normalized to look like such? And secondly, is this and correct me if I'm using the nomenclature wrongly, but is this a way to kind of feature select within your data set what's important and how to weight things and going forward?
Yeah, the best, they are normalized, and they are laid out just so you get a feeling of how important they are. So what's important, for example, if you look at one of these factors is like let's say almost a 3 and the other one is less than 1, then you could say that, all right, this factor is roughly 3 times more important than that one. So you could kind of use these numbers almost as like regression coefficients. So the higher they are, they're going to correlate to their value of importance, so to say. So if one, like the highest one is twice as the number of the coefficient is twice as high as the one below it, then that's telling you that it's probably twice as important, kind of, in a layman's way to describe that.
And I
Thanks,
think
David.
it's fairly logical too, when you look at the top 5 or 6 as a clinician, in other words, and you're trying to predict diabetes, yes or no, I would think that makes sense. Certainly blood pressure is a comorbidity. People with hypertension have insulin resistance. It's just part of the landscape, a genetic thing. And so again, it makes good sense, but I would agree with David that having information gain here is one of the easiest ways to get at what is the model looking at. Some of what I'm going to show you is a little bit more fuzzy. And also, as David indicated, don't expect these techniques to be exactly the same. In other words, now he's used the diabetes data set. I'm going to use the heart disease data set. But what I'm saying is they may vary a little bit. Chances are the top 3, 4, or 5 are going to be the same, but maybe the order will be slightly different. Just be aware of that. It's not a perfect science for a lot of different reasons. Other question, David, you want to click on the select columns because we haven't used that a whole lot. I just want to be sure that they know what you're doing there.
So what I'm doing here is, typically when you start out with the data, it might all end up over here in the left. So everything might end up in the left. Let's say if you just entered the data, what will happen, and if you connect the select columns widget to it, it might guess what's a feature, what's a target. But in this case, I just took everything out just to show you. Let's just assume that it threw its hands up and said, I don't know what's going on here. So you would take this data and say, all right, diabetes, yes, no is my target. All these factors over here, they're a feature, they're my X, and I'm going to take gender, and I'm going to move that down here, which is called a meta. So that's like a stratification column. So that is something that, you know, the rank widget and a variety of other widgets, they need some help to get started. And sometimes even in Orange, if they don't advertise that you don't need the select columns widget, but nothing is showing up in the algorithm box, you might want to go back and add the select columns widget, because that's telling you that somehow Orange is having difficulty identifying what's going on, what's an X, what's a Y, and what's a meta, or what's a stratified group.
The other thing about that that's nice is, you know, glucose really shouldn't be in this model, but it's so easy to just move it back to the left, move it out of there. So you ignore it, in other words, and run the model without it. So, you know, again, the select column allows you to do that real quickly compared to having to write code to do that, let's say.
And that's
So
just what I did. Yep. So you can
What's
see
the
now,
difference? What's the difference between a meta and the featured category?
a feature is typically a continuous variable, and a meta is a categorical stratification variable.
I see.
So it's-
And it'll automatically differentiate that red box and green box.
Yes.
Okay, thanks.
okay. That's great. Let's see. Zidane was here. Now I guess he's leaving. Okay. All right. Sorry to hear that. He'll be missed.
So Bob, you want to go back and then talk about the other
Yeah, and so I'll take.
widgets?
I'll
Can I
go
ask
ahead.
a quick question, please? It's
Okay.
for Hannah. Hi. I can't find the rank widget when I open Orange. Is it under Explain module or is it somewhere else?
No, rank should be, I think from my memory, actually under the very first thing. Now, correlation, they stuck under unsupervised learning. Don't ask me why. Let me,
Yeah, rank, if you just
let's see
right,
where I found. Yeah, rank is under data. Don't ask me why.
Okay, fine. Thanks.
Okay.
but
The other
easiest
thing,
way
by
to
the way,
find it-
just
Sorry.
a minor point is if you want to get rid of this menu, go to view and uncheck this, and it'll go out of your way. And you say, well, geez, how do I know? But the point is, if you right click the blank screen and you just put, let's say you want select column, put SEL, and there it is. So, you know, while the menu is nice, it's not absolutely necessary, okay? All right, let me go over the book and then I'll get back to this, you know, master flow thing. So thanks, David, because I think what we're saying is, even though there are techniques to explain the model, sometimes the explanation is as bad as the original question of how does the model work. So we'll go over a couple of them that we feel make good sense, but tell you ones that are a little bit more problematic, if you will. So let's go to the next one. And I have a little bit of scrolling trouble here. Feature important widget does something called permutation, which also means shuffling. And all that means is let's think about this diabetes column for a minute, or data set. There was a column there on systolic blood pressure, right? What if you changed, you know, you have a lot of values for each patient has a systolic blood pressure. Well, what happens if you go in and you shuffle and mix those up? Instead of patient number 1 having a systolic blood pressure of 120, it now is 180. And you mix it all up, you shuffle it or permutate it. The idea would be, well, what did that do to the model? If it didn't affect it much, then that predictor must not have been very important. And so you can go into that widget. Let's see if they show. No, they don't show it, but you can select the AUC, which would be generally what you would do for classification. And you would say, I want to see what factors really do impact the AUC, because if it impacts the AUC a lot, it must be important. Does that make sense? At least I hope it does. So this is how you set it up. It's in the workflow I sent you. This is the heart disease one. What comes up is major vessels colored, which is a terrible term, not by a clinician. It just means the number of coronary arteries that are calcified on fluoroscopy. Probably they lit up as a color. That's why it says color. And so these are the risk factors the feature importance widget picked up that it felt was important for the heart disease. And it makes sense, you know, but again, this order of putting calcified coronary arteries first is not necessarily going to be the same for another algorithm. This is for logistic regression. So be aware that that adds a little bit to the confusion. So what you do is you'd be very specific and say, using permutation feature importance and the feature importance widget and logistic regression on the heart disease prediction data set, it showed that the most important predictor was this major vessels colored. So just bear that in mind. It is not going to be the same for each algorithm or each technique to try to explain the module. That obviously further confuses things, but this one is easy to understand. I do think that the information gain on the rank widget, the way David set it up, if you're writing an article, that's probably what I would use to say, we felt these were the most important predictors, and you can give the score of the information gain. So that's basically it in a nutshell. You can choose something other than AUC, but for classification, AUC is the gold standard. Okay, the next one called Explain Widget. I'm actually only going to go over that quickly. Why? Because number one, it explains individual predictions. In other words, you want to go into patient number 5, who, let's say there's something weird about that patient. They're a 25-year-old with coronary disease or whatever, and you want to see how the model did with that one patient. This will give you that information. The setup is more confusing, as you can see, with a chance for error, but we tried very hard in there to explain the widget, how you set up the widget, how you set up the connectors. That's what these are showing you, how to set it up right. And then on top of that, you have to select the patient of interest. You go into the prediction widget. I think, what did I say? I predicted a 77-year-old man, I think. No, this is a prediction for a 55-year-old man who they said had heart disease, and the prediction using logistic regression was 1-0. So there was no doubt in the mind of logistic regression, this guy had heart disease. And so then you use a technique called SHAP and look at what it saw. So what this is saying is, if you have no vessels calcified, that's strong evidence against coronary disease. But for this patient, now, not the model, but for this patient, he had a lot of ST depression. Some of you are going to know that who tuned in, some of you are not. But when you do a stress test, you look for EKG changes, you watch to see if the baseline drops. That's what ST depression is. That indicates the heart's not getting enough blood. 5 millimeters of ST depression is like, uh-oh, turn off the machine. He can stop exercising. So this is what it saw. This is, I don't even want to get into that because I'm not sure why they say chest pain equal asymptomatic. But anyway, maximal heart rate, the significance of this is that people with coronary disease quit on the stress test earlier, so their heart rate was less. And so that was a factor that, you know, was important in this patient. And then no surprise, he had a reversible defect on his heart scan, showing that basically, in a nutshell, parts of the heart were missing when they scanned them under exercise, and then it recovered later and returned, meaning that he was lacking blood supply with exercise that returned to normal after exercise. So that's what a reversible defect is. lastly is the one that people talk about the most, but I think it's still a little problematic, called SHAP, or shapely additive explanation. Somebody jokingly said it's its own black box, meaning when I go to try to explain it to you, it's pretty confusing, other than it goes over each predictor and creates its own little model, so to speak. And then we'll show an example of that and the setup, if you will. So I thought I would choose neural network, which is basically harder to explain than a lot of the other ones. And we'd use the heart disease once again. So basically, let me go over what the significance of this. On the x-axis, you see a 0. To the right is positive SHAP score, if you will. And this scale can vary depending on what your predictors are. This could be a lot higher, a lot lower, depending. It's color-coded, so high means the value or how much this feature impacts the model, if you will. So red is really important. So the first one, and also let me comment that each one of these points is actually a patient. They're jammed together, if you will, but that single point out here is a patient. When they crowd together, it's a fatter line, so to speak. So in this first one, what it's saying is the presence of particularly multiple calcified coronary arteries is strongly favors coronary disease in that model. Negative works against it. But again, it gets a little bit confusing in the sense that, so the interpretation of the thallium here is a normal one is strong evidence in essence against it. And again, it gets confusing as you go down. There's some that are purple that make it a little bit more confusing, but it basically, it's either strong evidence against it having impact on the model, or if it's blue, it's low impact for the model in essence. So again, this is one that's also often shown. This is called a bee swarm plot. I just added that. That's the first time I knew what they called that. But my point is, it is a little bit problematic. It's not always crystal clear. It's clear that the first one is the most significant, and you hope that the color coding is easy to interpret, basically. And then this is that putting it all together discussion section. Go ahead.
Could I ask a question? Just going back to the previous plot, the red and blue one.
Yeah.
So does the thickness of the plot tell you how much more reliable that explanation is in terms of representation within that particular? I mean, there's more people there.
That just means more people. This I think for the calcified vessels is spread out wide because some people had one calcified vessel, 2, 3. This one may be 4. It's spread out more. I guess thallium being normal is a narrow, it's a 1 or a 0, basically, right?
Yeah, it's dictated by the actual test results.
So most of these are categorical, so they're not spread out very much. But the thickness is just where the patients group together. This could be 100 patients right here, okay? And then I'm assuming this blue dot is an outlier in a manner of speaking. Yeah. So this is somebody, what I'm assuming this is somebody that got their heart rate up to say 200 or something, at far above the next person. All right, so like I mentioned, we're putting this section in, putting it all together is kind of a summary of the chapter to be sure you really understand it. And I would suggest to you all that you go ahead and do this after the fact and see if you can answer it. And then what I will have is 17 is a data exercise with another data set to put some of these principles into play, okay, so you can practice them, okay? All right, let me do a little thinking. Are you all okay with the orange workflow? Is there anything else you want us to demonstrate? It's on your The OWS file I sent you, it's all there that you can play with yourself. So, you know, I think it's there. What I thought we'd do is just start on the chapter, the next chapter. And again, we changed it. Instead of being classification, we've changed it to supervised learning. So we wrap in classification and regression in the same chapter. This image actually was also developed by the computer. I think I said something like a nurse making rounds or some such thing, and this is what was generated. We may move these and change them, but I just wanted to again say, kind of interesting what happens now with computerized art. All right, so we're going to go over this, and we're looking at the big principles initially, the important ones, and that is to make darn sure you understand the difference between supervised and unsupervised learning. So for supervised learning, again, you know what you're trying to predict, and you have some proof, some ground truth. And I think I put here, for instance, an example, prostate biopsies being benign or malignant. Maybe you're trying to predict the image, the pathological slide of benign versus malignant. But, you know, say 3 pathologists went over these biopsies and they staked their reputation when they said it was malignant, okay? So, but in this data set, you have a column that says benign and malignant. You know what you're trying to predict in the model. You're trying to create a model so that when you get future data, not on maybe in this data set, but another patient or group of patients, that you then, you know, test on those patients. How does the model do? Does it do as well on these brand new patients it's never seen? But in this case, you know what you're trying to predict. And if what you're trying to predict is categorical data like benign or malignant, admitted, not admitted, that's classification. Remember that last column called outcome can also be called class. That's where the term classification came from. Regression is when the column you're trying to predict is numerical. Cost of living, you know, cost of an admission, length of stay. You're trying to predict glucose, which is a continuous number, for instance. That would be regression. So do you all understand that the difference then, when I say supervised, you know what you're trying to predict? Unsupervised is just, let's say it's raw data in the sense that you haven't nicely separated it into 2 categories, or there's no target, if you will. What you're doing is on an exploration to see if there are groups or clusters in here worth exploring further. So unsupervised learning is just a data set with no output. It's not labeled anything. Does that make sense? It's a big, and the 2 examples I use that are medical, more or less, is one was an article recently in JAMA where they use unsupervised learning on all their COVID patients in the ICU. And they wanted to see if they had any subphenotypes, meaning were there groupings or clusters? And the answer, there were 4 groups of COVID ICU patients. Group 1 was the most benign. Nobody was intubated, nobody died, nobody was mechanically ventilated. And group 4, you can imagine, many of them died, they didn't do well, and so forth. So that was one example of how you could use unsupervised learning. And as Anthony Chang would say, this is grossly under-leveraged. We should be using this as part of almost every new data set to try to see if you have clusters that you didn't recognize before. It's a nice tool. Another example was, and a lot of people are not aware of this, there is a website in the United States called County Health Ranking. And so every county is ranked in their state, first of all, in order, but more importantly, they're ranked in terms of things like income, education, smoking, illicit drug use, teenage pregnancy. You can imagine there's like 50 parameters, self-rating, which is actually surprisingly important. If a patient tells you, I'm not healthy, they're not healthy, be it psychological or physical. And so, okay, so in the state of Florida, there's 67 counties, and I'll make that data set available to you. But the idea was, I said, okay, what will unsupervised learning find in that 67 Florida counties? Well, it wasn't earth-shaking, but it was pretty clear that it lumped them into two categories, healthy and unhealthy. And it was pretty, when you looked at the sub, the actual columns, they made perfect sense. These were people that rated themselves not healthy. They were people that did not have as good a job, were less well-educated, on and on and on. And if you're the public health commissioner, you'd want to know that. So I'm just giving you two examples of that. So most of supervised learning, or most of machine learning rather, is supervised learning. And of supervised learning, most of it's classification. And under classification, most of it's binary. It doesn't have to be. In other words, binary in the sense it's like they survived, they died. But let's use an example that Hal would appreciate. Let's talk about an echocardiogram. If the ejection fraction is over 50%, that pump is working pretty well. That, I don't think anybody would argue that's normal. If the ejection fraction is 40 to 50%, that's borderline, okay? And if it's below 40, that's abnormal. So now you got three categories, okay? So that's multi-class classification. So it's a little bit artificial to separate these. Dave, I want to ask for any input you had. In other words, we could have used regression for the ejection fraction because it could be anywhere from 0.2 to 0.6. You could predict the ejection fraction, or you could take those and bin them, put them into buckets of low, medium, high, or abnormal, borderline, and normal. You could do either. There are some advantages and disadvantages between the two approaches, but I think there are times when we put things into buckets that are not totally logical. In other words, like iron deficiency anemia, let's say your iron level's 1 point from being abnormal. But so you lump it in the normal range. You see what I'm saying? So Dave, do you have any comments about that choosing? I mean, you can do both. You can run the model with both. So
the huge data set I have of home healthcare, for example, I play with this back and forth all the time. I have I have some continuous data, and I'll look at it and then I'll put it into small bins and then see if each of the bins are statistically significant, and I'll make the bin a little bit bigger, and I'll figure, okay, can I break it now down into 2 or 3 classifications and see if that makes more sense based on the profile of the curve. So yeah, based on the profile of raw data that is continuous, where you have the opportunity to turn it into classification, you could go back and forth, and really it's experimental. Yeah, you have to set the size of the bins properly to have enough data. And then once you have that set, then you can start to do the modeling that's going to make sense once you have the bin sizes set properly.
So thanks. So there is some trial and error. And the thing is, even when you go to, for instance, the University of California, Irvine data repository that has, I don't know, over 500 data sets, and you look at what they're used for, sometimes they'll say classification, regression, and clustering. I mean, they'll hint to you that you can do all three. So often a data set is used for one thing, but you could, for instance, that data set on heart disease, you could try to predict the ST depression, which is numerical or continuous, but you could also do clustering. So you can do all three. They're not mutually exclusive by any means. Just for the sake of completeness, though, reinforcement learning is a type of learning It came from the gaming industry where you have an agent like the Pac-Man and you have an environment which is like the maze. And this can be either machine learning or AI. You can have deep learning do reinforcement learning. In fact, when the Deep Brain won the AlphaGo, that project where it won Go, that was deep learning reinforcement learning. Semi-supervised is really kind of a blend of supervised and unsupervised. We rarely ever talk about that, so I'm not going to go over it. And transfer learning is where the model trains on an initial data set and uses that experience to do a prediction on something else. The best example of that probably is that so many of the models, certainly Google trained, was on ImageNet of 14 million images, and it uses that to actually classify things that are not all that related. And you say, well, how can that be? The answer is it trains on colors, shapes, sizes, borders, light, dark, you name it. So that's transfer learning, which is very important in deep learning, but not for what we're talking about right now. Just for the sake of clarification, very often people may change the output. Instead of making, say, the word cancer, they'll change it to 1 and benign to 0. Traditionally, the variable of interest in the output is labeled 1. It's usually the minority. There are fewer of them. And 0 is benign. But that is considered discrete. You can be categorical yet discrete. So somebody would say, well, wait a minute, that's a number. Isn't that continuous? No, because you talk about 1 and 0, not 1.5, not 0.5. So it's discrete. But computers, as you all remember, like to interpret ones and zeros. So that's why it's very common to see that last column that you're trying to predict as 1 and 0. Let's see.
Bob, have you showed them how to do indicator variables, dummy variables at some previous point where you get the ones and zeros broken out?
That I'll have to look if that's in this chapter. I'll be honest, I don't. The one how to coding basically was how we labeled it.
Yeah, one hot encoding, yeah.
Yeah, I think that's in chapter 2 that we've already done, I think.
Okay.
Some of the widgets, by the way, in Orange automatically do that. If you have a categorical value, it'll automatically encode it as numerical or as one hot encoding. All right, my goal here is to stop in a second. I wanted to just go over this table 6.1, and we'll get you a chapter here by the next time. We'll probably give you chapter 6 finished, polished, and ready to go, okay? This is just a table that shows you that many of the algorithms can do regression and classification. I've never seen this table, so I wanted to create one just to show you that many of them can do both. Sometimes they're tweaked. For instance, it would become support vector regressor if it does regression. But to make a long story short, many of these can do both. So I'm going to stop right there before we get to this exercise until next month. Are there questions about anything we've covered today? Is there anything in the Orange workflow that we need to go over?
No, I'm good.
Okay, because we'll obviously record this and I'll have it on the YouTube channel for people who are unable to make it, okay?
Thanks, Bob.
Okay, and if there's not anything else, I'll probably go ahead and close it down. I'm looking for the stop record button, pause, I guess.
Bob, just a request. Where can we get the later versions of your textbook? The version I have doesn't have some of the things you were referring to.
I'm sorry, what about the book? What were you saying?
The chapter you sent me before, this is the updated chapter which you are referring to now. where can
Yeah,
we
well-
have the updated chapter?
You do now have updated chapter 5. And so what I'm saying is by next time, I hope we'll have updated chapter 6 for you. Because we're going over each one of these chapters very slowly and rewriting them. So we're doing the best we can to give you updated information. And that's all we can do
Sure.
to try to revise this, okay?
It's amazing,
And where
Bob.
can we find the link, Bob? The link for this,
Okay, link for what though?
for the latest chapter, which you are referring to now. The one I have the Word document in the PDF, they are slightly older, which you had shared previously.
Okay, no, I sent one early this morning. It's in the WhatsApp. That's only a couple of hours old.
Ah, I might have missed it. Sorry.
Yeah, you may have missed it.
Bob, just to clarify, that's chapter 5 that you sent, is that right?
That is correct.
Yes.
Yeah,
But
okay.
that is the same exact that I showed you now, so it is up to date.
Perfect. Thanks.
Okay, so again, we'll have this available for you shortly. Okay, I'm going to go ahead and stop the share. And I appreciate your participation, and I'll have that posted. Let me see. Stop